Григорий Иосифович, трансляция началась, а вот iPad, похоже, отключился.
Да. Спасибо, что сказали. Да, надо будет это делать сейчас. Его. Непонятно, почему это он так делает. Попробуем еще раз. Так, ну вроде так, все нормально.
Угу.
So, okay. So, let me recall briefly what I said previously about polynomial representations and the Schur-Weyl duality. So I recall my notation. So these are representations of the group GLN, which are holomorphic. And this category is equivalent to the category of ordinary representations of a unitary group. And polynomial representations are the representations which can be realized in the tensor space. This one, we take the tautological representation in the space Cn and take the tensor power. And this is my notation for the corresponding representation in the tensor space. And it is, of course, in this category. And next, we consider the representation of the symmetry group, which acts in on this space by permutations of the tensors, of its copies of this space, is better to say. And the famous Schur duality says that the commutant, this is my notation for the commutant, that is the set, the algebra of operators which commute with our representation, is generated by this representation of the symmetry group, which acts by permutations, and vice versa. So because we have here completely reducible representations, the algebra generated by such a representation is semi-simple, and then the commutant is also semi-simple, and the double commutant theorem says that the double commutant returns us to the initial algebra. And next I recall how to the construction of certain highest weight vectors of irreducible constituents of this tensor space. So they are indexed by non-negative signatures. Non-negative just means that the coordinates are non-negative. And the highest vectors, these are not the only highest vectors, but these are some examples which suffice to describe all the irreducible sub-representations, all the irreducible components. There are multiplicities, so the highest weight vectors are not unique, but it's enough to produce some representatives of these highest weight vectors. They are constructed as follows. So take the Young diagram, which corresponds to lambda, and to fill it with the basis vectors as shown here. I mean that we take the tensor product of all these vectors, we get some tensor monomial, and then we antisymmetrize this tensor monomial over the columns. So this is an example. So we just start with anti-symmetrization. So here we permute these two vectors and with sign minus, and then we can further permute these two vectors and get these vectors with sign plus, and so on and so on. And in total, we get these numbers of summons. And this is my notations for the column length. So in this case, we have to take 3 factorial times 2 factorial, 1 factorial, 1 factorial. This is just the explanation of what means this anti-symmetrization. And an exercise is to show that such a construction gives us some highest weight vector. What means highest weight? This means that this vector is annihilated by the raising operators. The raising operators are this one, raising operators, raising operators, the ones which corresponds to the matrix units with I strictly less than J. Okay. So this is an exercise to just to verify this. Okay, and as a result, we get the following picture: the structure of a representation of this product of GLN and the symmetry group on this space. This representation is a multiplicity-free direct sum, of joint, one can say, joint representation of this group and this one. And these representations are indexed by Young diagrams with K boxes, and the length does not exceed capital N. So this is a representation which we already know in terms of its character. We know its character. The character is given by the Schur polynomial. We know it. And this is some accompanying representation which I did not discuss it, but from this result one can deduce there exists a certain representation of certain irreducible representation of a symmetry group. This is my notation for it, which is indexed by the same lambda. So this is the result of a Schur-Weil duality. But what next? Today I would like to explain two interrelated generalization of a Schur-Weil duality. Why we need a generalization? This is because the polynomial representations form only part of all representation. Not any representation is polynomial. So if you want to extend the construction in the spirit of Schur-Weil duality, we need to do something more. A natural idea is to take arbitrary tensor representations, meaning that we take mixed tensor spaces. What this means, we take the same tensor space as above, and this is the dual space. The dual space can be defined in two equivalent ways. This is the space E bar just means the space of linear functionals on E. And the next definition, which is equivalent, if you are dealing with representations of a unitary group, that is, if you equip this space with its canonical inner product, the scalar product, then the space of linear functionals can be identified in a canonical way with the same space, but with the conjugate complex structure, meaning that the multiplication by a complex number is given by the multiplication by the conjugate complex number. So these are two possible, a little bit different, but equivalent viewpoint on what is the dual conjugate representation. So here we have the tautological representation T, and here we have the one can say, anti-tautological or dual representation in this space, and we take the tensor product, here the tensor product, and we get in this way a family of representations which are indexed by two non-negative numbers, k and l. And these are representations of this group, which are still complex analytic. What means, why are they complex analytic? In terms of this group, this means that an element G of GLN, it acts on E as G itself, and on E bar, it acts as G transposed raised to inverse, okay? And on the unitary group, this just means that we take the bar over G, okay? So from this description, it is seen that it is still a complex analytic representation, okay? So these are all some trivial details, but they are really important to understand that the representation, I would like to emphasize again, the fact that the representation on this space is still complex analytic, not anti-complex analytic. So there is no problem. So we get in this way, this family of representation. And now the result, which I would like to state now, the proposition is that with all these representations contain together all possible irreducible representations of our category. How to prove this?
А содержит с повторами или нет?
Что ли?
Содержит с повторами или нет?
Да, конечно. I would like to emphasize, of course, there are some multiplicities, sometimes even huge multiplicities, but they claim that nothing is missing. If we investigate this family, all irreducibles can be extracted in some way from these representations, but of course not uniquely, not in a canonical way. So the idea is follows. It's convenient to switch from one language to another one. I mean from GLN picture to U, to the unitary group picture. And I recall the notion of a matrix element. So a matrix element is given by a choice of two vectors, xi and eta. It is a function on the group. In my situation, I want to take G in this group, in the unitary group. And this function is given by this simple formula. T, here T is some arbitrary. I'm sorry, maybe it's not a good notation because it's not a tautological representation in its, but temporary it is arbitrary representation of the unitary group. And what next? We remark that the matrix element of a tautological representations are simply the matrix elements of the group itself. And those of the dual representation are these conjugate functions, okay? And those from all these tensor representations, they contain all possible monomials which can be formed from these elements and from these elements. So what we get? We have a compact space. This is a compact space. And we have an algebra of functions which are spanned by these matrix elements. And this algebra of functions is closed under complex conjugation because of this bar here. And it separates points, it's obvious. So we apply the the Stonework theorem, which says that the linear span of these monomials formed from matrix elements, this is an algebra, it is dense in the algebra of all complex valued functions with respect to the uniform norm, the supremum norm. But because this is a compact space, this algebra is also dense in the Hilbert space with respect to the Haar measure for trivial reasons. And finally, we apply the Peter-Weil theorem to conclude that nothing is missing, that we catch all possible matrix elements of finite dimensional representation. So the conclusion is that this is just the end of the proof. So the crucial step is the application of this completeness, one can say, theorem, which says that the matrix elements form an orthogonal basis, which is dense in L2, so okay. But now the question, if you want to do something like Weil, we want to understand the commutant of this representation. So what is the commutant? So let's discuss this topic. To do this, I want to discuss the concept which is called the Wald-Brouwer semigroup. The Brouwer semigroups is a notion which was introduced by a great mathematician, Richard, or maybe German, Richard, because it was initially a German mathematician. He introduced in a paper 37 the notion of what is called now the Brouwer semigroup, but he did not introduce this notion. This notion, it's quite a natural version of the Brouwer semigroup. The Brouwer semigroup is something which is related to orthogonal groups. But the Wald-Brouwer semigroup is a similar object which is related to the unitary group or to the GLN, which is the same. And it was introduced in two papers, one by Turaev and the other by Koike, independent essentially at the same time. But in some sense, it is even simpler, a little bit simpler than the initial notion of the Brouwer semigroup. This is a beautiful paper, and I highly recommend to read it. It's in Annals of Mathematics. It's easy to download it. So, what is the definition of this semigroup? It is convenient to use a special interpretation for permutations. We will represent permutations by some graphs, some pictures, which is quite simple. So what you need? So fix K and consider permutations of a set of 1 to K. And take a copy of this set, 1 prime and so on, K prime. And we will draw pictures like this. So what we want to do, we consider perfect matchings. What means perfect matching? A perfect matching on the set of even cardinality is just a partition of the set into pairs, which are disjoint. So we put some elements in pairs. So as shown here, but the condition is that we join 1 point from this top level to one of the bottom level. So something like this. And this picture in particular represents the permutation which sends 1 to 3, 2 to 1, and 3 to 2. So it's quite natural. And so this is shown here. this index j is joined to some index I, if and only if the image of j by a given permutation S is equal to I. So here so think of this level as that of j indices and this level of I indices. Okay? So in this notation, the product of two permutations reduces just to concatenation of the corresponding picture. So we draw one picture which corresponds to an element S, and this picture corresponds to a permutation T, and then the product of S and T in this order is just obtained by taking this simple rule. We just concatenate the possible arrows, the edges in this order. Okay, so this evidently this rule just corresponds to the product of permutations in the natural way. Now the definition of a Wald-Brouwer semigroup. The Wald-Brouwer semigroup is as follows. Formally, its elements are represented by perfect matchings, so by pictures like this one, on sets of, we take one set, another set, which is its elements are denoted by these natural numbers with bar. Next we have, and these are on the top level, and these are on the bottom level. So we have this set, the disjoint union of this set and this set at the top. The j indices will be here, and the I indices will be here, and the edges are of two types. If they are vertical, then they are between this set and this one, or between this and this one, and they also can be horizontal. In the symmetric group picture, there are no horizontal edges, but here they are allowed. So these are horizontal, possible horizontal edges. So this is some example. So assume that k is equal to 3, L is 2. We have, say, 3 white nodes and 2 black nodes at the top. This is a little bit strange notation, but it will be clear. And their copies at the bottom. And this is the wall. This is the wall. This explains why it's called walled. This is some wall which symbolically separates this group from this one. So possible horizontal edges and this one. So an element is a picture like this. By definition, is an element of a future semigroup. But now we have to explain how to multiply two pictures just in the same way as before, just concatenation. So we take one picture like this and add to it some other picture which represent a second element and concatenate it. So we identify the nodes at the bottom level from this element with the corresponding nodes from the top level of the first element. First is here, second is here. Multiplication is in this order, from the right to left, okay? So we concatenate, and we get, this is an exercise that after concatenation, we get another picture of the same type, but with possible loops. There are possible loops which can arise from this horizontal edge. So assume that we have here something like this. some edges. Then we get a loop. At this moment, we have to ignore these loops. If you ignore these loops, we get just throw away them temporarily. Then we get exactly a picture of the same type. This is not difficult to see, just to think a little bit. And in this way, we get a multiplication just in the same way as for the symmetric group. But the only difference is that because of the possible horizontal edges, we don't get a group. There is no inversion, possible inversion, but we get a semigroup. So this is the Wald-Brouwer semigroup. The Wald-Brouwer semigroup, this is the definition. So this is some picture. You see what this is a picture, one element B, this element A, and we want to multiply them and get the element AB. So what we get? So we see we have this path, okay. Okay, and so we get, okay, so we get just this edge. This edge is preserved, it is here. Here there is a loop, as I explained, so it's ignored, and so on. So this composition just gives us this vertical edge, but in principle, the picture can be more involved, but the result is essentially the same. We get some other element of A, which enables us to correctly define a multiplication. And now the theorem, which says the following: the commutant of our representation in the mixed tensor space is generated by a certain projective representation of a Wald-Brouwer semigroup. So I have to explain what means projective representation. It's not an ordinary representation, but a projective representation. In principle, the definition is essentially the same as in the case of groups, but so assume that we want to define what means a representation, say, capital P of some semigroup whose elements are denoted as A and B. So if you multiply out two operators corresponding to given two elements, the result is not exactly, sorry, this is something which we have to erase it. It's not. So this is just a product, excuse me. This is just a product of A and B, but the difference is that there is some possible number factor, which I assume to be non-zero, which can arise. So this is an equality up to a scalar factor. And this scalar factor I want it to be a cocycle. In the case of groups, this is necessary. But in the case of semigroups, it's a little bit involved because in principle, these operators are not necessarily invertible. So there are some possible difficulties. Why I want only to insist that this function, this is a number function in two variables, A and B, I want it to satisfy these. I impose this condition. And if it is satisfied, so the definition is correct. So what should be correct? We need to have some associativity requirement. Okay, so because if you have a triple A, B, C, we can multiply out these elements in two different ways. First, we multiply A and B, and next we multiply with C. Or we multiply B and C, and next we multiply with A. And the result should produce the same factor in front of the product ABC. So this gives us this condition. And the requirement of the theorem is that the claim holds with a special cocycle. The special cocycle depends on n, which is related to GLN, and it is defined as follows. We take n raised to the power which equals the number of possible loops which can arise from the multiplication of two pictures. And then this condition is evident because then we have three pictures which are concatenated. And one can see that the left-hand side and the right-hand side produce the same number of loops. So we get this equality, and the number on the left is equal to the number on the right. It is equal to the n raised to the number of all loops which arise from this combined picture. So this is the theorem, but we need to prove it and to explain how to make this semigroup, the Brouwer semigroup, acting on the space of mixed tensors, which is not evident. So the step number one is just the definition of a future representation. We want to define operators. Let's denote it as follows. The operators which correspond to given two elements of a Brouwer semigroup. So given a picture A, we want to assign to it a certain operator which acts on the space of mixed tensors. So I want to explain now how to do this. To do this, take the basis. We need a basis. Here, the basis is quite reasonable. We just take the natural basis on E, E1, E2, and so on, and the basis on the conjugate space. These are essentially the same vectors, but which are viewed as element of a dual space. So a tensor which you want is such a tensor, where these indices are a range over 1, 2, up to capital N. And such tensors form a natural basis here. So let's denote this basis vector as the one with index capital I. So capital I is the element of this set. Okay. The K plus L product of 1 to n, of a set of n, first n natural numbers. So maybe it's a bad notation. I see now it would be better to write maybe. This is the standard notation in combinatorics, and this is notation from n. Oh, sorry. So n is by definition the set. Okay. Okay, so if you have an operator A, to specify it, we can just define its matrix elements. So these are the matrix elements of an operator, because these are indices of our basis. And this means the natural equation mean that the operator sorry, there is something wrong here. I'm sorry. So this means that the basis element number J is sent to a linear combination. No, sorry, it's okay, I'm sorry, excuse me. All this, it's okay. This element is sent into a linear combination of our basis elements with these coefficients. Okay. So to specify the operator corresponding to a semigroup element A, we impose the following condition. The matrix element with on the intersection of the row number capital I and column number capital J is equal either to 1 or to 0. We take 1 if any two indices what is this? Sorry, this is something wrong here. Any two indices joined by a vertical or a horizontal edge are equal to each other. Okay, and otherwise we have 0 here. So how to understand it better? There are some model picture. This is the case of a group element, a permutation from the symmetric group. This cross gives us the elementary transposition between this element and this one, and the condition is as follows. So look here. It is convenient to slightly change the notation. So rename this 1 bar by 4 and 2 bar by 5 to get some uniform notation, and likewise here. So this is J's, these are I's. So the condition is follows. The operator which corresponds to this picture is as follows. The matrix element is either 1 or 0. It is equal to 1 if J1 is equal to E2, which corresponds to G1, because these positions 1 at the J level is joined to position number 2 at the I level, okay? And also likewise for this edge. And for any other conditions are these ones, okay? So it's easy to see that it is really correct. It's correct. And this gives us some permutation matrix. But this is another example, another model example. Instead of permutation, of elementary permutation, we get this picture, which is in some sense similar to it. But the difference is that the edges are not vertical, but horizontal. And this means the following condition here. Equality between two J indices not the condition between 1j and some I index, but the condition is imposed on two indices on the same kind. This corresponds, look here, J3 and J5. This corresponds to this edge between one white node and other black node. Okay. So this I try to get some impression about the definition, but formally the definition was given. So I want to repeat: a cross between two colors of two nodes of the same nature, of the same kind, two white or two black, it corresponds to a transposition of factors, of two tensor factors here. So if they are white, we just transpose two copies, number R, say, and number S. Okay. This happens if these are two white nodes, and this happens if you have two black nodes, okay, corresponding to the dual space. But what happens in this case? In this case, it turns out, assume for simplicity that we have only two factors. So our operator that we want to explain, to construct, it is a certain operator on this tensor product of two spaces. And with matrix elements are given by this condition. Okay, so these elements is equal to 1 if and only if these two indices are the same and these two indices also are the same. It's not a permutation, it's something different. And this can be understood as follows. First, we want to interpret, we want to identify this tensor space, E tensor with E bar, with a dual space. It can be identified in a canonical way with the space of operator on E. Namely, given how to say, factorized, maybe factorized tensor, just a product of two vectors, one from here and eta from here. We assign to it a rank 1 operator on the space E, which is written here. Maybe it would be better to write it in the Dirac notation from quantum mechanics with a brackets, but I write it just as follows. What means this notation? This is the notation for an operator. It transforms a given vector to some other vectors. So given a vector, we substitute it here, take its product, scalar product with this, and we get some scalar multiple from of Xi. So this is a general form of a rank 1 operator. So this is just a way to identify this space and this space. And now what we get? We get some operator on this space. And these operators transform a given operator A to a scalar multiple of the identity operator. So this is essentially a projection multiplied by this no, it's bad. I'm sorry, it's bad. Excuse me. I need to correct it. take the trace of A, multiply by the identity operator. This is what I want to explain. So these are one number, another number, which this is just some scalar, universal scalar, and this is something which depends linearly on A. So this is a linear operator from A's to scalar operators. So this is a well-defined operator. Maybe it's better to repeat it in a little bit differently. This map is given as follows. Such a tensor product is mapped onto this one standard, which is represented just by the identity operator, actually. And if two indices are different, it's mapped to 0. This is essentially the same definition. So in other terms, without this interpretation in terms of operator, just in the initial picture, one tensor is mapped into another tensor. The picture is as follows. We take the inner product. It's correct because this is something which depends linearly on Xi, it's correct, and anti-linearly in eta, but eta is an element of a dual space with a conjugate operation of taking the action with a conjugate operation of multiplication by scalar. So it's correct. So this is called the contraction of tensors. We have a canonical operation of contraction. Okay. It maps this space to one-dimensional space, and the adjoint operator maps it back. And there is some multiplication by n, which is hidden here. So this, finally, we get some operator inside this space. So this operator, I repeat, corresponds to this picture. And it's evident that it is not an invertible operator, but there is no contradiction because it corresponds to some semi-group element, not a group element. So in principle, it may happen. What next? The next is an observation. It's easy, actually, that our semi-group is generated by these simplest elements from these examples. A cross, which corresponds to some transposition, a group element, a transposition inside one copy of a symmetry group, one symmetry group, or from our symmetry group. And this corresponds to the indices R and S, which are two white nodes, and these are possibly two black nodes. They have to be bigger than K. And finally, one simplest picture of such a type, where R is white and S is black. And this is easy. This is really easy to see, just from the definition of the multiplication in the Brouwer semigroup, in the Wald-Brouwer semigroup. The next step is to prove that the operators on the tensor space, which are defined as I tried to explain, they commute with our initial representation of a group GLN. In the case of the symmetry group, it was easy, but it's also easy to see in this context more general also. So again, the the operators which correspond to group element, to permutations, for them it's easy, the same, just the same as in the case of Schur-Weil duality. But what happens in the case of the mixed tensors? But just look at this picture. This row and this one, all of them, they are equivariant with respect to our symmetry. I mean, they are consistent with the action of our group. Here is the trivial action, and here is also trivial, because here we get, okay, so in another interpretation, we get the scalar operator. So, okay, it's easy. It's easy to see. So this step is easy. So we already obtain some set of operators which are contained in the commutant of our representation. And this is a less trivial step, that our construction gives us the whole commutant. Nothing is missing. How to prove this? And in this situation, it turns out that we can reduce this fact to the ordinary Schur-Weil duality. Even although we are dealing here with a semi-group and not with symmetric group, there is a little trick which enables us to reduce this claim to the ordinary Schur duality and polynomial representations. How to do this? First of all, the general fact which I already used, namely, if you have two complex Euclidean spaces, V1 and V2, Euclidean means just that you have a positive definite inner product. Then there is a canonical isomorphism between the space of operators from this to this and the tensor space. Okay, and how to see this? Just a moment. So assume that this is a scalar, okay? So on the left, we have the space of linear functionals. And then the claim is that the space of linear functionals is identified with the same space, but with the conjugate complex structure. So this is what I already explained. And it's a little extension of this claim. I repeat the definition of this correspondence. It's as before. To this, just pass from right to left. Given a tensor, here we assign to it a rank 1 operator from this space to this one. And apply this. We apply this as follows. So we start with a space of operator. One could write the endomorphism, the space of endomorphism of our tensor space. We write it in this manner as before. So we take one copy with a conjugate complex structure. Now we look more closely on this. This space is this one, this space is the same this one, but with a conjugate structure. But what means the conjugated structure? We rewrite this space again, and here we change the structure here and here, and we get this. And then we regroup these factors as follows. And the miracle, we get the space of endomorphisms of the non-mixed tensor space. So we get an isomorphism of vector spaces, which is defined in a canonical way between the space of endomorphisms of this space, mixed tensors and non-mixed ones. And what happens? If you have, we have to verify this more closely. If you have some matrix X, maybe I should write G as before, which is a unitary matrix, it acts initially as this tensor product of some copies of X and X bar. Or if we want to deal with G-ln, we have to take X transposed and inversed, okay? And under this isomorphism, we need to check that it is mapped to this one. This does not mean at all that the representations in this space are the same as the representations on this space. This is wrong. But it only means that the homomorphism of a group is essentially the same. So there is no contradiction here. So such a matrix is transformed to this matrix. Okay? Because this is simply something which is related only to the group without representation. Okay? So there is no contradiction here. And under this isomorphism, the operators from the semigroup turns into operators from the symmetric group. And there is again no miracle here, because this transformation just can be interpreted as switching. I mean here. We look at the picture which corresponds to the black nodes. And let's switch the top and bottom levels. And if you do that, we see that we get the picture, exactly the picture corresponding to the one for non-mixed tensors. Okay? Because our condition that these edges should intersect the wall just will means that this node at the top should be joined to some node at the bottom. So it's correct, we get something like it. And then our claim just follows from the sure-while duality. So this shows that indeed the commutant is generated by the operators corresponding to the elements of a Brouwer semigroup. Now we need to show that these operators form a representation of a semigroup, a projective representation. This is the last step, is to check that this correspondence that I defined to a semigroup element, we assign the corresponding operators, which is defined by the picture. It satisfies the condition, meaning that it is a projective representation with exactly this cocycle, this one. Okay, this needs some verification. It's not completely trivial, probably, but I would like just to give some impression why it should be true. So the problem is related to the non-group element. So assume that KL are equal to 1. So we have this elementary picture. And the operator corresponding to this picture is this one, I recall, this factor and this standard vector. And it's trivial to see that we have this relation, which just explains the origin of this factor. And indeed, in this case, if you take the product, okay, we get just this loop, one loop here, which corresponds to this simple factor n. The number of loops is equal to 1 in this case. So this is not a proof, just some indication. So this proves the result that I recall that the commutant is generated by a certain representation, projective representation of a Brouwer semigroup. But what's next? We again here have the completely reducible picture, so we can conclude that the resulting representation of a product of a group and a semigroup, there is nothing complicated to take a product of a group, a semigroup, we get some semigroup. So the representation of this object on the space of tensors, of mixed tensors, this space, is a multiplicity-free direct sum of irreducible representations, which are of the following type: some representation of GLA and some representation of a semigroup. And here lambda ranges over a certain subset of signatures, because we know that representations of GLN are parameterized by some signatures. And these are certain representations. We don't know yet what are these representations, but we only conclude they exist. They exist, some representations of this semigroup. And a delicate question is which lambdas are present here, occur in this decomposition. It's not clear. And the answer is known. There is a paper by Stambridge, by John Stambridge, but it requires some work. I don't want to discuss it. I want only to mention that there is some necessary condition. It's an easy exercise that if lambda appears in this decomposition, if it shows up here, then it should satisfy this condition. I recall that these numbers are possibly negative, can be negative, so this can also be negative, so there is no problem here. And there is some sufficient condition that if we take, if you represent our signatures by a pair of two Young diagrams, one responsible for positive coordinates and this one responsible for the negative coordinates, and if the number of boxes is equal to k and this number of boxes is equal to L, then the corresponding representations enters the decomposition of the representation in the tensor space. So this is another exercise. I will explain a little bit later. This will become clear. Now I want to mention that there is the notion of the Wald-Brouwer algebra. So far, I discussed the Brouwer semigroup and its projective representations, but this can be viewed from a little bit different point of view. Namely, we take some parameter denoted by R. I'm not sure it's a good notation, but okay. So take a parameter. It can be a number parameter, numerical parameter, or even a formal variable. And the Wald-Brouwer algebra, which depends on this number, this parameter. It is a finite dimensional algebra, if you ignore this parameter, with a basis indexed by the element of a Brouwer semigroup, and the multiplication, which is given as follows. If you want to multiply the two elements of the algebra, we take the product in the Brouwer semigroup and introduce some numerical factor, or some, if you want, something which depends on the formal parameters. R raised to the number of loops which show up in the picture corresponding to this multiplication. From the trick which I explained with switching of the nodes of a black nodes, it follows that the dimension is the same as the dimension of a symmetric group, so k plus L factorial. So this is a finite dimensional algebra. And it's a very interesting object. And there are a lot of works about the structure of this algebra, its representations, the discussion of the question when this algebra is semi-simple, but sometimes it may be not semi-simple, and so on, so on. There are some quantum versions, some quantifications of this object. So this is some topic quite interesting. And now I would like to discuss some related subject, which also produces some version, some extension of a Schur-Weyl duality, and maybe even more natural in some sense. It appears as follows. So I recall the definition of the contractions. These are operators which map this tensor space to another tensor space with K and L, which and we just subtract one here and one from L. And the definition is as follows. I recall it just. We pick one index from this set, one index from this set, and make the contraction. We just insert instead of this pair of tensor terms, the scalars, which just means that we pass to this different tensor space, this contraction of this type. Okay? So this operation kills two tensor factors. Okay? And I recall that under the isomorphism, this map is just reduced to taking the trace of the operator. I'm sorry. Okay, I don't want, but I have to make a little correction. Okay, I will correct it before posting these notes. Sorry. So the definition I want to explain now, the definition of traceless subspace, traceless tensors. traceless is just related to this interpretation. So the definition is as follows. Given a space of mixed tensors, we define its subspace as the intersection of kernels of all possible contractions, where R ranges over the white nodes and S ranges over all black nodes. A little observation, quite obvious, I think, is that this is in fact an invariant subspace. This is because these operations are compatible with the action, it's called diagonal action of a group U10 of GLN no matter. And now I want to state the result. It consists of two parts. One part is as follows. So in the invariant subspace of traceless tensors, the commutant reduces only to the symmetric group action. So the extra commuting operators which come from the non-group elements of the Wald-Brauer algebra disappear in this subspace. This is the first claim. The second claim is as follows. So on this space of traceless tensors, we obtain a representation of this object, GLN and the product of two possibly different symmetric groups. So this representation is again multiplicity free, and we are able to describe explicitly its structure. So we have, as before, tensor product of one representation from here, another representation from here. And again, we have some subset of indices, some subset of signatures, but this time we can describe it explicitly, namely the conditions that are necessary and sufficient are as follows. First, this condition, which just means that we can combine these two Young diagrams into a signature. And the next condition that the number of boxes is exactly K, and the number of boxes in this diagram is exactly L. And let's denote, it's convenient to introduce some notation from this subset, and let's write it as follows. This is some subset of signatures satisfying these two conditions. And finally, I would like to briefly indicate the scheme of the proof. How to prove this? The first claim, the one that only the group elements survive, is easy. Namely, this is an invariant subspace. Take its orthogonal complement, so we get an orthogonal decomposition, which is invariant. This space is invariant under the action of a unitary group of GLN. And this is also invariant. And because of this, it follows that the commutant on this space, on this invariant subspace, is some part. It must be induced by certain elements of the commutant on this space. But the later commutant, we know what are operators from the commutant on mixed tensors. It is generated by the action of a Brauer semigroup. But from the very definition of a Brauer semigroup, we see that if we take an element A, which is not a group element, which if it contains some horizontal edge, then its action on this subspace gives us 0. Its action is trivial. It produces nothing. So the only elements which really operate on this subspace, these are elements of this group. And when, also we have to note that this space is preserved by these elements. This is one more observation which is important here. Not only any operator which commutes with representation, with the representation in traceless tensor is induced by some operator, but this space is invariant under this one. Okay, and this follows again from the very definition, because if you permute, if you take some permutation from here or here, this just amounts to some transformation of a contraction operators. One contraction operators is transformed with respect to conjugation by this group element is transformed to another contraction operators. So the condition that the tensor is traceless is preserved by the action of this group element. So this is easy. This is easy to see that the restriction to traceless tensors just reduces the picture to the action of a symmetric group only. So this is very nice because we get something which is very similar to the Schur-Weyl duality, only permutations which appear in this picture. But the second claim, which is about the fine structure, the explicit structure of the decomposition, is more involved, but it's not difficult again. So this is just my notation. We denote the representation on the space of traceless tensor by this symbol. And the first claim is that it contains all irreducible representations which satisfy my condition. We recall that the number of boxes is exactly equal to K and exactly equal to L. And how to prove this? Just produce some highest weight vectors, which corresponds to such a signature. And the construction is quite similar to that for non-mixed tensors. Just take one and this one, and again anti-symmetrize over the columns. Just the same. And there is no overlapping between these vectors and these vectors. Not overlapping in indices, I mean. The indices which appear here and which appear here are disjoint. This is because the length of this and plus the length of this does not exceed n. And again, one can see that such a vector, due to this anti-symmetrization, such a vector is killed by the raising operators. But here the raising operators operate as raising, and here, because of this structure, they operate as lowering operators. Okay, so the symmetry is preserved here. Just the reflection about which reverse the order 1, 2, 3 up to n. If it is reversed, there is a corresponding symmetry between raising and lowering operators. Okay, so one can verify this, and this is a good exercise. And the next claim is that if some irreducible, if you have some constituent of this representation, then it imposes these conditions. So this tensor space can't contain irreducible representations if these two conditions, if at least one of these conditions is violated. This is also not difficult to see. And now it remains to prove there is nothing more. So we showed that this space contains all representations with lambda satisfying the conditions above. We need to prove that there is nothing more. So it's impossible that this tensor space contains some irreducible representations with lambda plus satisfying this condition, or this, or in case both these inequalities are satisfied. Why it's so? This is because these smaller representations are contained in smaller tensor spaces. And one can show that there is no intertwining operator from this tensor space to another tensor space. It's not necessary here to take traceless tensors if these indices are smaller than this one. And this is the end of the proof. And you see that there are some, it's not essentially difficult in the sense that there is the apparatus here is relatively simple, nothing extremely difficult, some nice application of the same sure duality, sure-while duality as in the case of non-mixed tensors. So I only want to add that initially Brouwer defined his duality, Brouwer duality, not for representations of GLN, but for representations of the orthogonal group. And in the case of the orthogonal group, the Brouwer semigroup is defined as follows. I just want to give a picture. So elements of a Brouwer semigroup are pictured like this. There are no division on black and white, so we only have some pictures like this. And the composition is defined as before, and so on. So the arguments are a little bit more intricate here because we need to apply some, it's not sufficient to use the sure-while duality. We need to apply some other results which are related to the so-called first fundamental theorem of invariance for the orthogonal group. And there is a parallel theory related to the symplectic group. So I don't want to discuss it in detail. I want only to indicate that all the story can be generalized to the orthogonal group and symplectic group. And so there are some uniform viewpoint on the Brouwer semigroup and on the traceless tensor realization also. And in the case of a traceless realization, the commutant is generated just by the symmetric group, as in the case of a sure-while. So I think this is a very nice subject, which shows that the general idea, I would like, maybe I will repeat it again and again, is as follows, some general principle. So what I would like to say, that there are polynomial representations of GLN, which is some very specific part of representation theory, some isolated, one can say, part of representation theory. But on the other hand, we have general representations of the GLN groups and representations of orthogonal groups and representations of symplectic groups and general representations in type A for series A can be viewed just as objects similar to representations of orthogonal groups or symplectic groups. And while polynomial representation is something specific, something special. So there is some parallelism between general representations of GLN and representations of they are similar to representations of orthogonal and symplectic group, but for them there is no analog of polynomial representations. This is some specific feature of series. So okay, so this is the end for today. Okay. I will